So perhaps if we now return to the question that we began this course with, what does data have to do with intelligence? Any fool can know the point is to understand, and the goal of understanding is to predict. The brain, as we have seen, is largely a prediction machine. It also controls our bodies, but it does it through prediction. And we've learned how business systems, web applications can use the techniques for predictive intelligence that we've learned in this course, which are looking, listening, learning, connecting, predicting, and of course correcting, which we haven't covered. So it's worthwhile recapping what we've learned in each of these elements, just so that one realizes that we've actually covered a lot of ground, and to highlight the most important points that we might have gone through. In look, we talked about search, a very important technique called locality-sensitive hashing, the relationship of search, PageRank, etc. to memory, and touched upon associative memories and sparse distributed memories, which we just realized are crucial to things like hierarchical temporal memory, which is the latest in predictive intelligence. We went on to listen. We learned about the naive Bayes classifier and the role of mutual information in figuring out which features are better features and which ones are not. We went on to learn. We looked at a unified framework for classification as well as clustering, rule mining, and then talked about how latent or hidden models can be used to learn features and classes together. In Connect, we covered reasoning, the semantic web vision, how rules can be learned from large volumes of text, Bayesian networks for reasoning under uncertainty, and finally in Predict, we've talked about linear regression, linear prediction, neural networks, hierarchical temporal memory, the Blackboard architecture, and of course in the end, an intelligent system also has to translate these predictions into actions through corrections, which involves optimization and planning, which we haven't had time to cover this time, maybe next time. Along the way, we also learned about the load element, how large volumes of data and processing can be executed on modern computer systems emerging from the web. We learned about MapReduce and the evolution of databases. So congratulations, we've really covered a lot and learned a lot in this course. Even if at a high level, I hope you all see how things fit together. My goal in this course has been to try to convey the big picture, how many different techniques are different ways of looking at the same thing, which techniques work well in which situations, and hopefully you'll be ready for some interesting challenges, which I'll point to in a minute. Before that, let me point out some deep research problems. First one is looking. It seems very simple, searching and indexing. But then think about what's involved in looking at data. When I look at a piece of data, I need to figure out a lot of things. What features am I going to extract from this data? What techniques am I going to use? What insights do I think I can get out of this? These are all reasoning elements. Looking at data involves reasoning. Today, all that is done by people. There are very few assistive decision support systems to help people look at data. On a more abstract level, I've already mentioned this, how symbolic reasoning arises from bottom-up data-driven techniques, be they neural or predictive, classification, etc., clustering. Where do the symbols emerge and where does the rules and reasoning emerge? Where does logic emerge? These things are mysteries which we simply haven't understood adequately. And lastly, any web intelligence system, real intelligence system like a human being, or any business intelligence system requires a purpose. I'm certainly not suggesting that a machine would acquire its own purpose. I'm not suggesting for a moment that free will is anywhere near our grasp in terms of coding it, but at least the level at which we code our purpose is today very low. We're actually telling the system the real pieces of the puzzle. We're telling it how to look, how to listen, how to learn, how all the pieces fit together. We're giving it the architecture. We're not anywhere near systems which learn how to put these pieces together by themselves if given a goal. For example, if you were to design a system which controls all the traffic in a city, along with self-driving cars, how would this system evolve? How would this system make use of better techniques to achieve its stated goals? The stated goals are very clear. It's given to we give the system its goals, but the system itself is hard-coded in terms of how it puts different techniques together to achieve them. It's not able to reason about how it's reasoning. It sort of comes back to my first problem about reasoning about looking. Can we give systems a higher level purpose and then let the systems figure out the sub-goals and figure out how different techniques are put together? I think these three problems are deep, extremely difficult to tackle. They can be looked at as pointers to very specific research problems in thousands of different ways. And for graduate students looking at deep problems in big data analytics or artificial intelligence, I think these are good pointers. For those of you looking for more practical challenges, I'd like to point you to Kaggle, which is a site where organizations, both governments and companies, post data and problems about that data and invite people to compete for prizes if one can do some great data analytics using that data. There are lots of competitions up there. For example, there's this one about online product sales, predicting the online sales of a consumer product based on its features. Some of that data I've used in the latest programming assignment. There are others about different topics, such as very large-scale data mining using big data posted by Best Buy. We're talking about mobile web data and figuring out which products a user will be most interested in. So I think that, with all the techniques that you've learned or at least been exposed to in this course, you're well versed to solve many of these data mining challenges, probably with a little extra reading and a little extra work. But you should be able to approach these problems, know which algorithms to use, which packages to look for, which kinds of techniques to apply. Well, I guess this brings us to the end of the course. Please do review this course on coursetalk.org, and thanks for being such a great class. I hope you've all learned something and are well poised to explore web intelligence and big data in other courses, in practice, or even embark on your own research. Bye-bye and enjoy.